Hello and welcome. Today we're going to be talking about finding a tangent plane at every point on a surface. So again, we're just going to do some examples and show you a little trick to find these tangent planes at every point in the surface. So the idea here is as follows, right? We have a surface, let's say this, like that, right? And then we have some coordinates x, y, and z right here. All right, and let's say I go out to a specific point. I have an x naught and a y naught right there, and I go up and I find the point that it associates with on the surface itself. And then I want to, so if I look at the surface is maybe curved around there like this, and I find that tangent plane like that, right? So the tangent plane, of course, will have a normal vector. But I can think of this normal vector as actually a function of the point x naught, y naught. Okay, and so I want to see now if I were to move, if I were to go to a new point, if I were to now, go over here, so let's say I have a new point x naught, y naught, I move it over here to this point here, and there's the surface. Of course, there'd be a new tangent plane right there. And the normal vector, of course, would be pointing in a slightly different direction, right? Right. So you can think of this like sort of like maybe a snowboard going over this a surface of snow, and the board itself is, of course, going to kind of rock and roll and adapt to whatever the surface is that it's on, right? So we want to find out how to get this. All right. So in general, the idea here is we have some function z is equal to f of x comma y, all right? And we know that the tangent plane is going to be at z naught, which is going to be equal to f of x comma y naught, right? And then we have to compute those partial derivatives. And I'll call it, we'll say this is fx at x naught, y naught, right? We have to compute all of these things. We need to compute the z naught variable, and the slope in the x direction, and the slope in the y direction, right? And again, now, once we have all that, we can now go in and see about this thing. So we know that the tangent plane is this. Z is equal to z naught plus fx of x naught, y naught times x minus x naught plus fy at x naught, y naught times y minus y naught. Okay. All right. So this is what we call the linear function. Linear function approximation at x naught, y naught, right? To turn it into a plane,
what do you want to work on now?
A plane equation, what we do is, all we have to do is now subtract over the z variable. So what we have here is 0 is equal to minus 1 times z minus z naught plus fx x naught, y naught times x minus x naught, okay, plus fy of x naught, y naught times y minus y naught. Okay, so this looks pretty good, but we can see clearly that the normal vector then has a really special look to it. What we have here is it's going to be fx, x naught, y naught, fy, x naught, y naught, and then negative 1. And that's that key thing here, is that the z component is always going to be the same. It's just going to be negative 1. So here is our formula for that normal vector, right? I think that's the best way to represent these surfaces and finding that normal vector. All right, so now let's just do an example. Okay, so first let's look at this example, and this comes from number 15 in section 11.4. We have the function 2x plus 3 over 4y plus 1. So clearly y cannot be equal to negative 1/4. Okay, so that's clearly a point where that's going to be a point of non-differentiability. Okay, but aside from that point, so if this is my f of x comma y is equal to z, the point is, let's see if we can find out what the surface is. So in number 15, what it really asks is for the linear approximation at the origin. All right, so let's just do that one, and then we're going to expand on it and do some more things with this formula and see what we can find with it. See if we can find, so that I'll call it part A, and then part B is find the plane equation at every point x naught, y naught. Provided that y naught is not equal to negative 1/4. Obviously, that's a point of non-differentiability. Okay, so let's see if we can find it. So let's just do the first one. So let's compute f at 0, 0. That's going to be 3 over 1 is equal to 3. Cool. Right, now fx. We have to take the derivative, and it's going to be of the numerator, and so we're going to have, let's take this carefully, 2x plus 3 all over 4y plus 1, and that's going to be, remember that the 4y plus 1, that's just a constant with respect to the derivative of x. So I can do this, and then what I'm going to get is 2 over 4y plus 1. Okay, there we go. So fx at 0, 0 is going to be 2. Okay, cool. All right, now let's find fy. This one's going to be a little bit harder. And here we take the derivative with respect to y of the following thing, 2x plus 3 all over 4y plus 1. And now it's the 2x plus 3 that comes out front. Odin. So what we have here is going to be the 2x plus 3 is just a constant with respect to this thing. And what we're going to get is a 4y plus 1 quantity squared in the denominator, right? Times negative 4. Okay, cool. So now what we're going to do, of course, is find f of y at 0, 0. And that's going to be equal to, let's see what it is. So it's going to be 3 over 1 times negative 4, which is going to be equal to negative 12. Okay, so those are our values. If I put these all together, I find the following, that f of x comma y is approximately equal to 3, that's my z naught value, plus 2 times x, that's the fx value, minus 12y, and that, of course, is the fy value. Okay, so there's my linear approximation. Okay, so the linear approximation, of course, is only going to be accurate near the origin. Okay, so I think that's clear, and again, this works the same way as you would for a function that's only of one variable. The idea is that if you're nearby the origin, a linear approximation should be pretty good. Let's now follow up on this and figure out, so if that's my z value, let's now figure out what is the normal vector at 0, 0. Right, all we have to do, of course, is move the z over, and we're going to get 0 is equal to 3 plus 2x minus 12y minus z. Okay, well, you can see right there what the normal vector is. The normal vector is going to be 2, negative 12, negative 1. Okay. Right, so there we go. That's what we've done. What I want to do now is collect up my things, and now what I want to do is a new problem. Now I want to find n of x naught, y naught. I want to find the linear, the plane equation for all x naught, y naught that are allowed. Okay, so this is pretty straightforward again too. The idea here is you're going to have you're going to set 0 it equal to 0, and then you're going to have negative 1 for z. That's always there. This is the z slope. Okay. Well, hold on. I'm going to back up actually, and I'll put the z at the end. We'll do everything in x, y, z in that order. Let's look at the f of x. So the f of x is right there. We know it's equal to, that's what the derivative is equal to. So all we have to do is put that as a 2 over 4 times y naught plus 1, right? Times x minus x naught. Okay, perfect. Plus, now we have to look for this is fy right here, is sitting right there. And now I have to put that for the slope in the y direction. So that's going to be negative 4 times 2x naught plus 3 all over 4y naught plus 1 quantity squared. And we're going to multiply that y minus y naught. Okay, and then finally, minus 1 times z minus f of x naught, y naught. Right, so that is the plane equation. This is sort of like that plane. This is the plane that's defined at every point on the surface. It's sort of like the snowboard. The snowboard that's going over the surface and constantly changing its orientation as you're changing x naught and y naught. Okay. Hopefully that gives you some more interesting insights in how this works and how to make calculations. All right, I'm going to pause. I'll stop this video now, and we'll do another one shortly.